In this video, we are going to learn how to use a system of inequalities to solve a real-world scenario. So first example is your city's cultural center is sponsoring a concert to raise at least $30,000 for the city's youth services. Tickets are $20 for balcony seats and $30 for orchestra seats. If the center has 500 orchestra seats, how many of each type of seats must they sell? So first, let's break down this problem. We know that we need to raise at least $300,000, and we have a maximum of 500 orchestra seats that we can sell with a seemingly unlimited amount of balcony seats. Now, looking more closely at the problem, I see that each balcony seat is $20, and each orchestra seat is $30. So I know that if I'm charging $20 per balcony seat ticket, and $30 per orchestra seat ticket, together that must be at least $30,000, which just means that this total should be greater than or equal to $30,000. I don't want it to be less than that amount because that's my goal for this concert. Now, I also have this limitation. I do know that my orchestra seats orchestra seat tickets has to be less than or equal to 500. Because I can't sell more than 500 orchestra seats. So knowing all of this, if I let X equal the number of balcony seat tickets, and I let Y equal the number of orchestra seat tickets, I will end up with two inequalities. I'll have 20x plus 30y is greater than or equal to 30,000. And I will have y is less than or equal to 500. So if I wanted to graph to find these solutions, I would need my 2x plus 30y to be in slope-intercept form, which I can do by subtracting 20x. Give me 30y is greater than or equal to negative 20x is greater plus 30,000. And I can divide by 30 on each side to get y is greater than or equal to negative 2/3 x plus 1,000. So my system of inequalities is y is greater than or equal to negative 2/3 x plus 1,000. And I have y is less than or equal to 500. So in order to graph this, I'm going to need to count by hundreds on my x and y in order to actually fit these big numbers like 1,000 and 500. So along my y-axis, I'll be counting by 100 every time. And on my x-axis, I'll also be counting by 100 every time. Now, in order to graph this blue line, my y-intercept is 1,000, and it goes down 2 over 3, which in this case will be down 200 over 300, but that still is the slope. And this is greater than or equal to, so it'll be a solid line, and then I will shade above the line. So everything above it. And then I have y is less than or equal to 500, so y is always 500 for this line. So I have a horizontal line at 500. Put in a few dots to keep track of where to put my straight edge, and this will also be a solid line. But in this case, instead of shading above like the last one, since it's less than, I will be shading below this line. You'll see here that my solution region is on the bottom right over here. And again, it's always important to check, but any combination of tickets in this green region will meet the goal of $30,000. But if I wanted to check a point, here's a point here at 1,400. If I were to plug that in, I would have y is 400 is greater than or equal to negative 2/3 times 1,000 plus 1,000. Excuse me, 400 is greater than or equal to 600, negative 600, and 67 if I round to the nearest whole number, plus 1,000, which gives me 400 is greater than or equal to 333, which is correct. And if I check the y value, it is for sure less than 500. Less than or equal to 500. So this would be a solution to the system. That means that entire region is true. And this just goes to show you that sometimes a solution to a problem might not be one particular set of numbers, but like a range of numbers. Now let's look at one more example. A pizza parlor charges $1 for each of its vegetable toppings, $2 for each of the meat toppings, and you want at least 5 toppings on your pizza, and you have $10 to spend on toppings. So how many of each type of topping can you get on your pizza? Now, this isn't just one answer. There could be a range of answers that make this work. So what we need to figure out is using $1 for each vegetable topping and $2 for each meat topping. We need to come up with a system of inequalities to represent the situation going on. So I know I have at least 5 toppings, which means that vegetable toppings plus meat toppings must be greater than or equal to 5, because I don't want any less than 5 toppings. Now, money-wise, I could spend $1 per vegetable topping. And I'm charged $2 per meat topping, so 2 times meat topping. But together, that total cannot be more than $10 since I don't have more than 10 to spare. So if I let X equal the number of vegetable toppings and Y equal the number of meat toppings, I end up with these two inequalities. I'll have x plus y is greater than or equal to 5. And then I'll have x plus 2y is less than or equal to 10. Now these aren't in slope-intercept form, but that only takes a step. So if I were to subtract x, I'll get y is greater than or equal to negative x plus 5, which is now in slope-intercept form. And for the other one, if I were to subtract x, I would get 2y is less than or equal to negative x plus 10. Then divide by 2. Y is less than or equal to negative 1/2 x plus 5. That is now in slope-intercept form. So from here, I can go ahead and graph both of these inequalities. And since these numbers are more reasonable, I don't have to count by hundreds like the last problem. I can just count by ones. So 1, 2, 3, 4, 5. And then a slope of negative 1, so down 1 over 1. Solid line, and I'm going to be greater than this line. So everything above the line. The other one has the same y-intercept, but the slope is a lot shallower because I go down 1 over 2. And this is everything less than that line. So I seem to overlap between these two lines. Now one thing you're about to notice me do is I'm going to stop right at the x-axis. The main reason being is my vegetables, represented by the x-axis, normally I couldn't get any negative vegetables, so to go below this x-axis means I would have negative meat toppings, which doesn't make any sense. I'm going to stop there because I can't really have negative toppings. But there's my region, and again, if I want to check to make sure that I am correct, I'm going to pick a point within the space. So this is 1, 2, 3, 4, 5, 6. 1 is a solution within the space. So checking 6, 1. I'll have 1 is greater than or equal to negative of 6 plus 5, which means 1 is greater than or equal to negative 1, which is true. And then 1 is less than or equal to negative 1/2 times 6 plus 5, which means 1 is less than or equal to negative 3 plus 5, which is definitely true because 1 is not greater than 2. And again, you get that series of solutions that exist within that region, give you lots of options. And again, even these points that are on the lines themselves are also solutions that I could use. It doesn't have to just be in the middle of it. It could be anything along these lines since we include them in our solution with the equal sign. And that's how you use a system of inequalities to solve like a real life problem.